Good morning, everyone. Welcome to yet another session of X and AI Genomics Hackathon. Uh, we'll try as much as possible to adhere to rules and regulation of the hackathon and keep the time so exhaust we don't exhaust much of your time as well. All right, without further ado, I will just go straight up to the attendance calling. I hope everyone is there. Okay. Currently, just 11 participants. Well, this is 11 o'clock already, and I will just give the grace of 5 extra minutes before I call on the attendance. So if you have anyone in your team that is not here, kindly reach out to them to join us as we proceed. All right, 5 minutes grace. Okay. Over the weekend, we open up the floor for people share their um to share their expression regarding the hackathon and how it's gone so far, what points they feel like quitting, and what else? The their capacity to do better and what keeps them going. So a lot of people have shared their opinion on that, and yeah, some are commendable, some are touching, and someone also lost someone. Condolence to everyone. Okay, so today's section is going to be more like an interactive section where we address every other thing we'll be doing for the rest of the week before the final announcement is being called. I can commend everyone for doing their best or putting in their best so far. You know, it's a competition at the end of the day, and only few will be selected. So in never which way it comes to you, if you happen to be selected, you have done a very good job and a fantastic job. So if you haven't been selected, uh, if you don't happen to be selected, right, you did well as well. But you know, at the end of the day, someone might have done better than what you've given. So I don't want you to see it as a disappointment. I mean, you've given it all your best you have, but for some reason you couldn't ace over some people. So it's also commendable for you for coming this far. I mean, it's a fast-paced program, and that's not the end. I mean, the group has been carefully selected to be group of five. That means whether you're leaving or whether you're coming, your group still remains active. We'll still try to keep it active as well. So that being said, you can still support your team in whichever way you find, even though you're not selected. So that shouldn't make you give up on any aspiration or anything. I mean, more so, this isn't the end of the program. Another version is going to be coming up. So you have the opportunity to prove yourself better. Now, I'm just giving you heads up because no matter how much you like, not everyone will get to the final stage. It's just the way it is. All right. That being said, okay, let me go on the attendance. Currently, we have 17 people on the list, and I said I'll be giving you 5 minutes extra. So we only have 3 minutes to go. So at the clock of the time, I'll just call on the attendance. Now, the topic for today is XR and AI. You know, we've been talking about XR and AI genomics hackathon, and we've not mentioned anything around AI, right? Now, how will AI help us solve this or help us work faster? You already know there's ChatGPT which makes works faster, and with that you can apply a lot of innovation to what you've been doing. So I will carefully show you an example with Unity. I have my Unity loaded already. Once the attendance is done, I will just quickly brush on that for the next 30 minutes. Okay, this is 11:04. All right. So our attendance method is going to be a bit different today, just to make sure we don't exhaust much of our time. Now, before I start calling the attendance, I'm going to share my screen so everybody can see what I'm seeing. Now, before it gets to your name, if you're seeing your name, just be prepared to answer present. And Chooks, please, I hope you are ready for us. Please help us note the people that are present. I'm going to share the attendance with you as well so that you can tick as I'm calling. Thank you very much.
No
Okay.
problem on that.
Okay, yeah, quick one. Okay, confirm if you've received the attendance list so we can get started.
Yeah, I've done that.
Okay, all right. Now I will share my screen so everybody can see the attendance list for themselves and be ready to make a call for their name. All right. Okay, can everyone see my screen?
Yes, sir. Yes,
Okay,
sir.
all right, that's good then. All right. Okay, this is the attendance. So I'll make it bigger so everyone can see clearly. I'll begin by calling. So starting with team one, Messi Tebamifo, Ejiro Obrit, Jomiloju Adeboyejo, Adegborite Ayokunlemi, Samuel
Present.
Zaron, Benjamin,
Who said
Onondo
present?
Adeniran Sodiq, Afolayan G. Oluwole, Akande David, Alex M. Kiniu, Anna Undono, Awodi Abdulmujib, Awodi Abdulsamad, Bamidele Favor, Clement Ojo, Dr. Give, Famuyiwa Emmanuel, Fanny Olakunle, Ahmed Sherifuddin, Jagede Jua, John Victoria, Johnson Mayokun. As well, when you answer your present, try and drop your name on the chat so we can keep track of it as well. Thank you very much. John Victoria, Johnson Mayokun, Joseph Tuizarimana, Ignatius Emmanuel, Olamilekan, Olowoniyi, Dunamis, Oyedikachi Anthony, Shafiulai Usman, Stephen Jeremiah, Toyin Fowowe, Zainab Tofela. I'm done
Zainab
calling
should
team one.
yeah.
I'm done calling team one. If you're not in team, if you're in team one and you didn't hear your name and you're present right now, just drop a chat and your name. Drop it on the chat. Drop your name on the chat and the team you belong. Sorry, okay, you're already in team one. Okay, yeah, still drop it on the chat along with your team. Then moving on to team two, Jonathan Wisdom, Oladile Ibukun, Olamide Williams, Olofin Oluwatoke, Ono Joy, Ugoma, Peter God bless, Sabitus Salisu, Kane, Selbo John Kuju, Stephen Awa, Tracy G. Duncan, apologies for the wrong pronunciation. Wahab Ayomide, Oyedele Oluwatayo, Awa Abubakar, Damilare Taiwo, Usman Zakari, Akinwale Aremu, Oluwadare Victor, Abdul Malik Aliyu, Alpha Gulak, Beli Ibukun, Bukoye
Present, sir.
Mary, Ekoto Peace, Emmanuel, Ekeka Eromosili Felix, Goodness Ekpoto. That's for team two. If you're in team two and you didn't hear your name, drop your name and your team in the group chat. Sorry, in the chat. Moving on to team three. Ibituwase Oluwabukola, Isaac Addison Aduk, Kolawole Ayiti, Lana, Ngogu Misengu, Oluwafunmilade Afolabi, Oluwapelumi Solagbade, Omar Ahmed, Orimolade Tinu, Teslim Lawal,
Teslim Lawal present.
Tusingwaya Catherine Adekunle Sowole.
Present.
Okay. Balo Falowo. Dairo Ogunjob.
Present. Bimini Ifalo is present.
Okay. Tebafo Tola. Abdullah Akinade. Adeyemo Kilechi.
Adeyemo Kelechi present.
Okay. Adeyemo Kilechi. Akinde.
Okay, Gaffa.
Please, Taiwo Ogunjobi is present, oh, please.
What do you say?
Okay,
Taiwo
so
Ogunjobi
people
is
that.
present.
Okay.
So can you guys reach out to your team members and tell them they should join this meeting?
All right.
We've done that
Okay.
already. And then some of them are joining.
Okay,
Thank you.
that's nice. That's nice, yeah.
All right. Augustine Favor. Bonin Ngeku Navis. Caleb Otudeko.
Present.
Right. David Uduala.
David Odola is present.
Okay. Ebu Rachel Pius. Pai Mildred Buyo. Francisca Umambisi. That's for Team 3. If you are in Team 3 and you didn't hear your name.
Francisca is present.
Okay. If you are in Team 3 and you didn't hear your name, kindly drop your name in the chat section and your team. Okay, so moving on to Team 4. Alade Gideon.
Alade Gideon is present.
Okay. Gani in favor. Olaniwaju Osiga. Ayomide Jegede. Mustafa Okoyemi.
Mustafa Okoyemi is present.
Okay. Alobu Ejofo. Andrea Milena. Yeah, okay. Andrea Milenia. Ayomide Adegoke. Amzat Abdulaziz. Buklis Womp. This person. Okay, let me flag this. Okay. All right. Clinton Idausa. Eniola Alex.
Present, Eniola Alex.
Okay. Ramos. Ezinwere Dorcas. Idowu Ayomide. Ipinlaye Joy. Jesuranti. Kehinde Emmanuel. Korede Kolade Max Vet. Yawun New. Northern Bleed. Well, okay. Olakunleyin Adebusuyi. Oluwapelumi Jacob. Oluwaseun Amore. Onoseta.
Present. Onoseta is present.
Okay. Pelumi Dairo. Platus. Estekiola. Temitayo Oyedele. This person is not present. Please note that.
Present.
Okay, Temitayo, you're present. All right.
Yes.
Samuel Oluwa David. Moving on to Team 5. Samuel Oluwa David. Danny your Titilayo. Daniel Titilayo, Rome Odinaka, Ezrim Daniel, Sikirola Adebuye.
Present, sir. Sikirula, present.
Daniel is present.
Sikirula is present as well.
Okay. Sikirola, okay. Okeleye Samson. Oh, Bami.
Present,
Okay.
Okele.
Bamilosin Daniel. Tiwatope Olorunsola. Abdulbasit Hamza. Akwa Festus Tava. Christian Udeze.
Present.
Christian, okay. Udeze present. Egui Kai, apologies for the wrong pronunciation, but gift is gift online.
Okele
moving
Samson
on.
present.
Okay. Okunleye Samson.
Present.
Sir, you did not mark Sikirula present. Okay, right, sir. So, no, you have not marked it. Sikirula Adebayo is present, sir.
Okay. Elizabeth Wamoni, Emmanuel Oluwa Sise, John Joy, Mosisi Uguja,
Present.
Naima Okoyemi Idris, Pelumi Ademo, Perfection Popular, Triumph Onabu, Tomisin, Fikayo Olabisi, Oluwafemi, Oluwayinsolami, Oluwayinsolami, Sustain, Tamiko at one. Emmanuel, MKT Tonic at then John Joy. So that wraps up our attendance. So let me check. We have 34 participants here. Let me cross check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Just move
Good morning,
on.
sir. Sorry, sir. John Victoria is present on my network, sir.
Okay. So
Team one.
if what you can do now is just drop.
Team 3, you didn't mark David Odola present.
Okay, Chooks, please attend to that. So if you are currently online and you didn't check your attendance, just drop it on the chat to be noted. All right. So I will just stop. I will close this up so we can move down to the business of the day. Going by the time, really, let me check the time. Okay. Yeah, this is 11:18. So I have about 20 minutes to burn. So let's quickly get things together here. Okay, let me move to my Unity. I hope you can still see my screen. Can you still see my screen?
Yeah.
Okay.
Yes, sir.
Okay. All right. Let me move in my Unity windows back here. I think for some reason I couldn't access it over there.
Yes, sir. We can see your screen. So
Right to this moment, you can still see my screen, right?
yes.
Yes, sir.
Yes, sir. We can.
Okay. Can you confirm what you're currently seeing on my screen?
Unity scene.
Unity canvas.
Unity scene. Okay, good. All right. So the highlight for today is XR and AI,
Unity
right? Now
canvas.
we keep talking about XR and AI genomics hackathon, and we've not really touched on the AI aspect of it. Now, how can we bring in AI into what we've been doing so far? It's very simple. You can leverage on AI in your design pattern, in your UI, most especially, then in your monologue. When you're creating a sound, when you're adding sound to your stage, how do you get these sounds? How are you able to access sound? Or are you the one doing the recording, the audio recording before you put the sound? No, it's far easier than what you've been thinking. Now, the very simple way you can get this, you can achieve this is first, let me demonstrate this to you. Now, we have first, I'm going to be using two AI model here. The first one is going to be ChatGPT, while the second one is going to be okay. This is text to speech 11 labs. You must have heard of it. You must have heard of it. Now, just to wrap things up, first, let's go to ChatGPT. Let's create a monologue for our scene. So for instance, let's say you're moving into a lab. Okay, you're entering a lab. You want a sound, you want to open up introduction, like you're welcome to so lab. This is what goes on, this is what is happening, this is what you're here to do. You understand? That will give people sense of direction and instruction. That will give people sense of direction and instruction on what to do and what they are here for. You know, most times when people put on the headset, they lost control. You can't even control them. It happened several times when we have visitors come over to the institute and we give them a pair of headsets like, okay, you take this and experience what is happening. With laid out instructions sometimes, or sometimes you're trying to get them to understand what they need to do. But at that point, they are so captivated by what they are seeing and they can't even listen to you. They are in another world. It's a virtual reality at that point in time. They are no longer experiencing what you're experiencing. They are experiencing something different. So you're trying to control them from the outside, what will be met with obstructions. Now, how do you mitigate this? That's by creating voice prompt instruction in your scene. Let's say, for instance, when they move closer to the refrigerator, they get a voice prompt that says, open the refrigerator. Drop your test tube inside the refrigerator. Or maybe when they come into a scene, they get a voice prompt that tells them exactly what the scene is about. Now, for instance, moving into a lab scene can be different from moving into a molecular interaction scene. So when they enter a lab scene, they should get a voice prompt that is telling them, you're welcome to so lab scene. This is what you're here to do and that. Now, I will just quickly demonstrate how you can achieve that. Now, first thing I want to open is my ChatGPT, like I said earlier. I'll be using two AI model. The first is ChatGPT. Now, this ChatGPT, we can just give ChatGPT a prompt. Now, you can either use paid ChatGPT or free version. Either way, it works. It should deliver. Now, I'm going to be using a new chat. Now, to save us time, I will just use my dictate because I think that's the best way you can use ChatGPT now, rather than typing and taking much of your time. So I'm just going to give ChatGPT a voice prompt to take action on it. Now, I will just go ahead. I wanted to generate an audio monologue for a virtual reality scene. The scene is going to be a lab scene. Now, I want the audio monologue to be expressive and to come up with a cool introduction and instruction that should be taken in the lab scene. So what I've just done is give ChatGPT a monologue. So I want you to generate an audio monologue for a virtual reality scene. This scene is going to be a lab scene. Now, I want the audio monologue to be expressive and to come up with a cool introduction and instruction that should be taken in a lab scene, right? Now, I will just click OK and watch ChatGPT generate this monologue for us. Now you can see ChatGPT has generated a monologue for us. The summary monologue is just saying sound cue, soft background, home of lab equipment. So it's already telling you how you can make your scene come to life. So it's giving you things you need to add to your scene, like home of lab equipment, faint beep in the distance. For the Unity dev that are here, I think you already know how to add sound to your environment. Okay, then now this is telling you calm, confidence, slightly. We'll get to that later. Then the prompt, the monologue is welcome to Welcome to the ACEGID virtual lab, something you experience. Now, this is audio. This is what you'll be listening to when you enter that scene. Now here, take a moment to look around. Every surface, every instrument, every blinking light has a story to tell, and you're about to be part of it. In this space, precision is everything. Before we begin, remember these key rules. Handle all virtual equipment with care. Your actions here mirror the reward. Follow each step closely. Sequencing is a dance and timing matter. Keep your eyes open for prompts. This will guide you through each procedure. Today, you will walk through the process of preparing and running a genomic sequencing test for sample collections to data analysis. Yeah, for sample collection to data analysis to covering the code that makes life possible. Ready? Step forward and let's make science comes alive. Now, this prompt is really okay. Then what I will just do is I will have it copy. I will copy it from here because this is the exact what we want to work with. Now, I've copied it. The next thing I want to do is now work with the second AI model, which is the 11 labs. So I already have it saved here, but you can check the link. Let me copy the link and drop it right in the chat so you can experiment with it. So I'll have it copy now. Let me copy this. That's it. So I will just quickly drop it in the chat. Okay. What's happening here? Okay, I've dropped it in the chat. Now let's proceed. Hold on. I know what is happening. So it's preventing me from using. Okay, this solves it. All right. Okay, just back to what I'm doing. Now, this is the 11 labs. What do I want to do? I want to generate a text, right? I've copied the text I want to generate. Now, let's have it reload. Yeah, okay. Okay, I'm not exploring. I want to hold on. Boom. Okay, text to speech. And I want to clear this. Let me have this cleared away. Okay. Everything is well set. Now, I'm just going to come here. So part of the things you can explore here is voice changer. You can record your voice, you can add sound effects, you can do voice isolation, you can do all sorts of things, but I think it's limited to some extent because currently I'm using the free version. But until you have a fully subscribed version, then that is when you can explore a lot of things. But with this free version, there are things you can also achieve. You're not limited to all these things. So I'm going to delete this. Now, this is for a first-time user, this is what it's going to look like to you. This is exactly how it's going to look like. Then you will get a prompt that says, type your text with audio tags like laughs to turn into express speech. Now, I'm just going to paste the audio monologue I copied from ChatGPT earlier. So I've copied this. I'm pasting this. Now you can change different speaker. It has capacity for you to change from one speaker to the other. You can use a female. This is Rachel. This is a female speaker. And then let's just say I want to add another speaker here. Then I'm going to change the speaker to, let's say, Liam. Let me use Liam. So I've changed to Liam. Now let me break this into halves. Okay, so I will just cut this and put this here because I want Liam to also take part of the monologue. Now we've split our monologue into two. we split our monologue into two. Now let's just generate it and let's hear what it sounds like. So we are currently generating the monologue. In about a minute, it will be done. So it's done.
Welcome to the ACEGID virtual lab.
It's done generating the monologue. Yeah. And it's still loading though, but I will just track it back so we can have it played and everybody hear what it sounds like. So confirm if you can still hear me.
Yes, sir, we can.
Yes, sir, we can hear you.
Okay. So
Here, science isn't just something you read.
let's
Welcome to the ACEGID virtual lab. Here, science isn't just something you read about, it's something you experience. Take a moment to look around. Every surface, every instrument, every blinking light has a story to tell, and you're about to be part of it. In this space, precision is everything. Before we begin, remember these key rules.
Handle all virtual equipment with care. Your actions here mirror the real world. Follow each step closely. Sequencing is a dance, and timing matters. Keep your eyes open for prompts. They will guide you through each procedure. Today, you'll walk through the process of preparing and running a genomic sequencing test. From sample collection to data analysis, to uncovering the code that makes life possible. Ready? Step forward and let's make science come alive.
You can see that is the first generation. That is the first output. It's giving us two outputs at the same time. Now let's play the second output. Let's see which we're going to choose.
Welcome to the ACEGID virtual lab. Here, science isn't just something you read about, it's something you experience. Take a moment to look around. Every surface, every instrument, every blinking light has a story to tell, and you're about to be part of it. In this space, precision is everything. Before we begin, remember these key rules. Handle all virtual equipment with care. Your actions here mirror the real world. Follow each step closely. Sequencing is a dance and timing matters. Keep your eyes open for prompts. They will guide you through each procedure. Today, you'll walk through the process of preparing and running a genomic sequencing test, from sample collection to data analysis to uncovering the code that makes life possible. Ready? Step forward and let's make science come alive.
So just as the voice played, you can see, well, we've been able to generate two audio. So I'll just proceed to downloading the first one, but I think I prefer the first one better than the second one. So this is our audio. It's already downloaded. It's downloaded already. You can see it's over here. Then now, quick one. Let's have the video load in our scene. Now, this is our I've just started the play into this scene. I just started the play into this scene, and what we'll be doing now is adding an audio to the plane because we don't have much objects yet. So I will just click on the plane and come here, add the component. Then I want to look for audio source. Audio source. Okay, this is my audio source. I've added the audio source. Now, what do? We need to bring the audio back to Unity. The audio we want to have in this space. We have to bring it to Unity. Now, how do we do that? Usually, I prefer people working on a structured outcome. So what I'm just going to do is I'll be creating an empty folder here. So create, then folder. So this folder I'm creating, I want to give it a name. Where is it? This is my new folder. I want to give it audio. So I've created an audio folder. Now I'll open it up. Then what I want to do next is bring the audio we downloaded over here. So let me open my file explorer and have it open. This is my download section. And then this is the audio. Now I'm dropping it, I'm dragging it and drop here. So our audio is already on Unity already. Now I will close this. Now let's go back to this audio. Now, audio source, this is asking for audio source. So we're dragging this and putting it here. You can see. So this is everything you need to do. Then what you want to come down for the settings, put it in a 3D spatial blend. What this does is make it bring the environment to life in sort of a way. If you are here, it's mimic a 3D environment where the sound is coming from your background, from your back. If you're facing that side, the sound is coming from your back. If you're looking at this, yeah.
They can't see your screen. I think.
Okay, you currently can't see my screen.
Yeah,
I can see your screen.
I can see your screen.
So why is he
your
Emmanuel?
screen.
Emmanuel is saying he can't see your screen.
Oh, it's probably network from his end.
Okay.
All right.
Yeah.
So let me just rush this down. Now this is the now to 3D. I believe you understand what 2D is and what 3 dimension is. Then audio reverb mix, okay, it's okay. The pitch, we can work with the pitch, we can reduce it, we can increase it. So to the best of ourselves. And then this is the volume. You can make it low, you can make it high. The priority, you can set the priority. Now, how do you want this audio to play? Is it on awake? Now, what on awake means is once you enter that scene, once the object is awake in that scene, like currently now, this object is live in this scene. If I come here and click this, the object is gone. So in a situation where you don't have the object in the scene, you won't hear any audio. But once the object comes into the scene, you begin to hear the audio right away. And what else? You can change this. You can make this work on different, right? Like you can make this work differently. You can set trigger to it. For instance, maybe on collision, you can use scripts to add collision object. Like, okay, let's watch out for a game object. Let's say, for instance, this is a game, or you're playing a pickpocket game, or okay, in reference to lab, you're picking up a pipette and you're taking sample. You want to attach a sound to that pipette alone, not other things. So now the pipette is supposed, let's say for instance, it's supposed to give a click sound. Now, would you want that click sound to also apply to fridge? No, fridge is going to come up with another sound. Now, let me just rush this up so we cover up on this. Now, after adding this audio to it, put on play on awake. Do you want to put it on loop? When you put it on loop means it keeps repeating. It keeps repeating, but it won't work for us. So we'll just say we won't do this. Hold on.
Hello. Am I the only one that can't hear Mr. Jafar? Anyway.
Yeah, please hold
Me
on.
here too. I can't hear him.
I think we lost him there on the network.
All right.
Apologies, I had an urgent call coming in, so I had to put my this on mute. Apologies for that. Okay. So I will just wrap this up. Now, because I'm not with my headset, I will just play this directly so you can hear what it sounds like. So let me activate the scene. So with these current settings, yeah, we are good to go. You can change it to your own taste. So the scene is loading up already. Okay, yeah, for some reason, let me choose output. It's not playing the sound out. Let me stop this. Hold on. Output. No. So this is not, okay, currently this is not working because I'm not connected to the headset. So in your own case, if you are using the headset, it's automatically going to play. Let me see if I can do something around this. Let me check my audio outputs. Okay, audio speaker, earphone, yeah. Outputs. Okay. So, okay, everything is working fine. It's just not playing out because I'm not connected to an headset. So in your own case, if you're connected to an headset, it's going to play automatically. It's going to take a lot of setting up to have me connected to the headset. So yeah. Because of time, because we've been time conscious today, I would like to stop here and give Mr. Dio the room to take over from here. Now, basically, what we're doing today is just to put you on what your project is going to be. I think you've had the opportunity to, we assigned tasks to everyone last week, and which some people delivered, some people did an excellent job. Some people need to work on their performance. But at the long run, Mr. Dai is going to come on and brief you at large on exactly what you'll be doing and how you have to get it done. And yeah, I'm wishing you all the best of luck. Mr. Dio, are you available?
Yes, I am.
Okay. So yeah, the floor is yours.
All right. Okay. Can everyone hear me?
Yes, we can hear you, sir.
All right, wonderful. So, briefly, we just want to talk about the task for this week. The task for this week will just be to unify every, well, the scientist, the Unity developer, and the Blender artist. And after this meeting, we will compile a file detailing the task and send it to you guys. But the task for this week is not going to be specific for maybe scientists, Unity developers, and Blender artists. Albeit I see that the Blender artists and the Unity developers might have more work on their hand. But what is this task going to be? It is to create a scene based on the tasks from last week. I know Team 1 worked on nucleic acid extraction, and Team 2 worked on their own PCR and all like that. So at the end of this week, your task or what the result of your task will be a scene that shows a scientist carrying out that particular task in a lab that is well equipped with all of the facilities, equipment, and resources you need to carry out that task. So what it means is that, take for example, Team one, having understood the principles and the steps that need to be carried out to conduct the assay on the scientist's part, you have to communicate this to your Unity developer to create a scene where nucleic acid extraction can be carried out using all of the required equipment and the right biosafety containment. And standardly, all of this work that is meant to be done will be at the biosafety level 2 lab. And this applies to all teams, although the biosafety level 2 is more applicable to team 1, since they are the ones that were working in code, simulating, working with
We cannot hear you again, sir.
His network trip off. He will be back shortly.
Hello, everyone. Sorry, I had a network glitch and I was logged out. So, like I was saying, can somebody just tell me where I you guys stopped hearing me?
Yes, sir. You were trying to explain the tax that you'll be giving to us this week. You're talking about, for example, like Team 2 now, what we presented last week, maybe on PCR, we presented on PCR. So the Unity developer will work on the procedure just like the way we are going to carry it out in the lab from the step one to the last step.
Okay. Okay, wonderful. So you scientists are kind of like the team judge of the product of your work. Because I believe you guys know some of the limitations you have in terms of equipment and all of that. So you'll be your internal judge to see that, okay, if I see this scene, would it give me an understanding of this particular concept in molecular biology before we now bring and submit it to the uh what's the name, uh to the entire participants and mentors. So on the presentation day, it will just be a play of your work, what has been done, you play it, and I think we should limit the video to about 10 minutes, but I and the other mentors will discuss the time frame for all of this process to go on, and we'll get back to you on that. But like I was saying, the scientists in the team are the ones that will be like the internal judge in the teams to be able to say, okay, if I watch this video, does it communicate this thing to me? And if I view this in a VR headset, for example, will I be able to understand process? So yeah, simulating a scene where that process is being carried out. And then we can then build on that maybe when we come around for participants that will be on site next week, and then we can work on simulation properly. The individuals can then carry it out. But you view the scene where this thing is kind of it is not kind of, it's being carried out. So it's kind of, your result is kind of like a tutorial video. So the writers on the team will be working on the monologue. There will be a monologue, like a voiceover telling what the scientist is doing. So what it means is you have a scientist, one or two scientists, maximum of two scientists, working in that scene and carrying out the procedure. So what you're essentially doing is creating kind of a tutorial video of what is going on. But the viewer must be able to know what is going on from the beginning to the end. So that is the task for this week. We would work with our other mentors and put this into text so that you can put it into perspectives. Into perspective. So one thing I would advise is that everybody should work in unity with one another. So this is not a team for just scientists. This is not a work. This is not a work. I mean, this is not a task for just scientists. This is not a task for just Unity developers. This is not just a task for Blender artists. This is a task that is representative of the team. So what it means, you need communication from the scientists to the Unity developer to create the scene, then the Blender artist to develop all the models that are required for the Unity developer to put into the scene. So more or less, the Unity developer is one bringing the ideas of everybody into one scene. So you're working together, where everybody is working together to achieve one common goal. And what that means is, I foresee that the issues that you might be having is your Unity developers who are in a different field, not fully understanding what the science behind it. That's where you as a scientist need to communicate it in simple terms. And also, I must note, this task should be communicated in simple terms. You don't have to go into details of the nitty-gritty. I know you're a scientist. You want to show that you know the science. But as we talked about it in our earlier classes, that science should be communicated in simple terms. And the goal of all of this is to be able to communicate science to even the layman that does not know some of these things. So what it means, somebody that will put on a VR set and not have any knowledge of science, but can understand what is going on in that particular scene. And if brought into another scene where he or she is to carry this process out, the person can be able to carry it out as simple as possible. So try to uh, reduce scientific jargon and put it as simple as possible. I would recommend you guys watch videos online of how a scientist communicates science to different levels. There are videos like that on YouTube where a scientist is communicating science to a 5-year-old, a teenager, a an undergraduate, a graduate student, a postdoc person, and an actual researcher. But we are looking at the level between like a 5-year-old to maybe a college student. So as simple as possible. Do we all understand the task? And we have questions. All right, Damilare Taiwo. Damilare Taiwo, please go ahead.
Good morning, sir. Can you hear me, sir?
Yes, I can.
Also, you are
Sorry,
trying to explain biosafety level. Okay, sir.
before you. All right, sorry, I just quickly needed to attend to someone. So go ahead, please.
Well, thank you so much, sir, for the opportunity. So I want to ask
Yes.
about, you are trying to also explain biosafety level as well.
Yes.
Yeah, also. And number two, I want
Okay.
to ask, yes, sir. I
Oh,
want
you
to
want me
ask
to build
about,
on that?
sir?
You want me to build on that? So,
Yes, you were explaining that before your network, before something came up then.
all right, all right. Okay, and also what?
Secondly, about the assignments, sir. So, because for example, like team two, we work on 4 different PCR. Are we going to do those 4 in just 10-minute video, or just we pick one PCR, sir?
Okay. Let me answer the first one. So the first one is about biosafety level. And this is highly likely, not even likely. It is mainly on the owners of team one because we are assuming that you are working with live pathogen or at least working in biosafety level two to protect yourself. And what makes a biosafety level two is just a cabinet. So that means that biosafety level two cabinet has to be in your scene. And every
Okay.
work that will be done for extraction will be done in that scene.
Oh,
However, for anything after extraction does not require biosafety level 2 because your pathogen has been denatured. There's a technical word for it that eludes me now. But in simple terms, your pathogen is dead. You just have the DNA or the RNA of your pathogen, and you're working with that. And your pathogen is somewhat not infectious, although some individuals might have the the some arguments with that, but that's not for this moment. So I know all what this means is that for every scene, team one to team five, there should be the appropriate biosafety, the appropriate PPE. The scientists will understand what I'm saying. The appropriate PPE. That means there should be basic lab coats for all of the scenes that the scientist is wearing. Lab coats, the necessary lab coats, face mask, and gloves. So that's for number one. Now for PCR, yes, you have to simulate for all of different types of PCR that you're working with. However, there are common steps in those things. I don't want to start suggesting to you. I think the onus is for you guys to think of a way to unify all of these steps and just bring out a product uh, that summarizes everything. I have a concept in mind, but I don't want to give you guys the explain. I will leave that as a bridge for you guys to cross. But yes, you should be able to simulate all of the different types of PCR. So, have I
okay,
answered
sir.
your question?
Yes, thank you so much, sir.
Okay. So, Gemini follow. Please go ahead. Gemini follow. Please, are
Yes,
you
good
there?
morning. Good morning. Yes, good morning once again, sir. I really appreciate all your effort and appreciate all the mentors here, there, and my colleagues. I want to ask that the tax for this week, would you please, like last week, also state them in plain terms and language for us to be able to follow through and carry it out? Just like last week when we have, okay, this are exactly what the Unity developers are doing, the Blender artists are doing, the scientists are doing, so that at least we have a template of steps and procedure of what we are working with and then the goal at head. Thank you, sir.
All right. So, like I said, the task for this week is not about for scientists, for Unity developers, and for Blender artists. I'll call this task a unifying task. There was one goal of this hackathon when it was publicized that do you want to know how molecular biology is conducted in a lab and you don't have the necessary tools. The goal of this hackathon is to bring forth a simulation in which at the end of this hackathon, anybody that comes maybe to ACEGID, the product of this hackathon can be viewed in a VR headset and person can interact and have an understanding of how genomics is being conducted in IGH, for example. Are you with me? So there's a point in which you have to unify the entire team together. So the if I would say the team leads of this project will usually be the scientists. Why? Because they're the ones that understand how some of these processes are conducted in the lab. So the Unity developer is to help them bring this process into life. And while the Blender artist is meant to help them, is meant to give the Unity developer the tools to bring all of these things into lab. For example, simulate the equipment that is required so that the Unity developer can put it into his or her scene. Are you with me? So there is no specific work for one person, but everybody is meant to work together to produce a particular product. Are we together? So what it
Yes,
means is that the quality of your product will be reflective of how the scientist was able to communicate the
yes.
procedure to the Unity developer in simple terms, and also how well the Blender artist is able to simulate life
Equipment.
representation.
Yeah.
Yes, live representation of, take for example, the equipment that are being used, or the scientist that is carrying it out. Just like you view animations and you can see that, oh, this animation is relatable, it looks like real life. I believe that's what the Blender artist uh is meant to do. Although it's not my expertise, but that's what my other mentors who have experts in that can clarify that for me. But that is the goal of it.
Thank you, sir. So while the writers are involved in the monologue, voiceover and
Exactly.
things like that. All right, all right, all right. So
Exactly.
these are the things I wanted you to list out or spell out so that we'll be able to know this is what we are focusing. And then all attention is on the scientists. What do they want us to bring to life for them?
Exactly.
As Unity.
Exactly.
Thank you so much, sir.
All right, you're welcome. So I'm looking at the chat now, and someone is saying, summary, are you saying something like having a scientist model character doing the task or assignment that we did last week? I think yes, I've answered that. So the answer is yes to that. Another one says, are you saying, okay, sorry. Okay, I think that came in twice. When is the submission date for the task, sir? We'll get back to you on that. Well, it might be either Wednesday or Thursday, likely maximum of Thursday, but we'll get back to you on the Discord channel for that. So you have a short time. I know it's a lot of pressure, but we also have a short time. So someone asked, what about a team without a blender artist? So I'd like to confirm, which team does not have a blender artist? If your team does not have a blender artist, your team captain should please speak up so that we can work on that. Or if maybe your
Team
blender
4.
artist has been dormant. Team 4 does not have a blender artist. All
Yes.
right. Okay,
Okay.
we'll note that.
Yeah, Mr. Dio, sorry to cut you short, just to say something to that. Every team was assigned a blender artist. So for some reason, maybe your blender artist didn't participate or ghosted the group. That could have happened. But regardless, let's host a meeting tonight. I've created voice channel for each group. So just go into the group chat, the voice channel group chat, and open up a voice channel. We'll discuss that over today. So we can move forward on that. And then regarding the assignment submission, this task is to stretch you thin. It's not, we are not giving you, we know some of it can complete what you have to do right now, but we want to see the best you can put in, how far you can go, and what are the possibilities of you completing it just within the short period of time. Now, note that this task is what you, for the qualified candidate, that is this same task, they will continue when they come on site. So your contribution from now matters till the end of the hackathon. Do you understand?
I believe we've understood that. And also, to add to what Mr. Gafar said, all of these tasks are also to enable you to familiarize with all of the steps and the things you need to do to get to a climax or a climax of a project. So the project that you're going to be working on when you come on site is not entirely different from what you're working on now. It's you using tools from the knowledge you've gained from the 2 weeks, and then participants will be selected producing it on site. That's just how simple it is. So as much as there's a lot of pressure, it's also giving you the tools that you need when you're going to be working there. So Mr. Gafar, someone has a question for you in the chat. He's asking if the 11 lab you used, was it a premium? I suppose it's a software. Was it premium?
Okay, the one I use actually is freemium. It's not premium. So the premium will give you a certain word count a day. And I'm sure you can't exhaust it because myself, I've done a lot of projects around it and I have not had the chance to exhaust it once.
All right, I think that answers the question. So, any other question before we move on to the next lecture or the next session? So I take it that there's no other question. The next session will be conducted by Dr. George, a postdoctoral fellow at the Institute of Genomics and Global Health, IGH, and he will be giving you an overview of genomic sequencing technologies. I believe the scientists will gain a lot from this, but the Unity developers and Blender artists should please also listen so that you can be able to relate to some of the work that is being done in the genomics lab so that you can have an understanding. And I believe it also help you in understanding the concepts and why all of these things are necessary. So I'll be handing over the mic to Dr. George.
Thank you so very much, Sadayo. Really privileged to be here. And thank you for the great work you've done. I mean, I came in a bit to listen to the interesting discussion you guys have. And good afternoon, everyone. I don't know if you can hear me from there.
Yes, we can hear you, sir.
Oh, great. Thank you so very much. Okay, so I'll just quickly share my screen. I didn't really know the extent of how the discussion is going to be, but I just prepared something small. But I was thinking we're going to have more of a discussion rather than just teaching and lecturing and all of that, since I've been told that almost everybody in the group is like a big boy and a big girl. So we would also just discuss. And we'll also just have a little discussion, and then probably we're going to take questions and answers and all of that. So we'll see how we go from there. So let me just share my screen and then see how we go from there. Okay, so sorry about that. Can we all see my screen?
Yes, sir.
Okay, great. So this is just a little overview of next generation sequencing, just basic introduction, the principles. I don't know if you've already been taught this. Dr. Dio is one of the experts in this. So whatever I'm missing out there, he's going to help us chip in, and then we also see how we go from there. So my discussion is just going to be a little bit more of the wet lab, and then we're also going to have a little bit on what to do with the dry lab, right, regarding just a few bioinformatics workflow, but I might not really go in detail, so this is not really a detailed, just to give you like an overview, general guide on what to do. So basically, next generation sequencing, it's a way that has really helped us sequence a whole range of DNA and RNA. Could be clinical samples, could be, from a whole tons of data. Sometimes we go back to, you've heard like fossil record, samples collected 2,000-3,000 years ago, but with this technology, we've been able to like glean more information and then generate billions of data, not just millions of data in different fragments. So one of the key interesting part of next generation sequencing is that it's unlike before where we had what we call Sanger sequencing. I don't know if you've had, I don't know, Dio, have they been told about Sanger sequencing? Sorry, the class, have you had anything regarding Sanger sequencing?
Yes, we mentioned it in passing.
Okay, great.
It was used for the Human Genome Project.
Great. So unlike the previous, like the Human Genome Project, before then to get the human genome took like years using Sanger sequencing. But now with NGS, there's rapid turnaround time, and the process is way cheaper compared to what was done before. And then it's been used in not just in genomics, transcriptomics, metagenomics, which I'll just touch on that later at the course of the discussion. Sorry, I think I missed something. Okay, so I might flip my slide to our preparation. So there are different types of platform. So briefly, I'll just introduce us to some of the different platforms. Each of the platform, they have their strength, they have their weaknesses, and they also have their strong points. And then we have the Illumina, which is more or less like the short read sequencing, and it's seen as there's high level of accuracy and also high throughput. You also have the Ion Torrent, which gives moderate reads, small application. And then PacBio is also, one of the technology that is very robust, and it's actually based on long read sequencing. And the interesting thing about PacBio is its high fidelity or high accuracy, if as the case may be. You also have the Oxford nanopore sequencing, which is also the ultra long reads. And the interesting thing about this is that you could sequence this in your bedroom. You can use this, depending on where you are, even in the field, in real-time sequencing, right? So it's really made sequencing a little bit more easier to go with, unlike Illumina platform that you need a specialized room and all of that. So go on. Sorry, my slide was a little bit twisted, and then this is just a summary of what I wanted to show you, the workflow, NGS workflow that we use regularly in our lab. I mean, I've used this a couple of times too, which I believe some of you, especially those in the dry lab, where you go through the DNA extraction process, right? Your starting material could be RNA. So if your starting material is RNA, then you have to reverse transcribe the RNA to get a complementary DNA. But if your starting material, depending on your research objective, it could be probably human genome, which is made up of DNA, you could start with the DNA. If your focus is maybe mRNA, or when I mean mRNA, messenger RNA, for those of you that are not biochemists, or the workflow is on RNA viruses. So you would have to do like convert the RNA to complementary DNA, right? So depending on which workflow you're starting with, and you prepare your libraries, which I believe you may have been given basic introduction. So first you fragment your library, and then you tag, and then you take it down to step 3, which is the machine, depending on which platform. If it's the Ion Torrent, if it's the Oxford, which is the PacBio or Illumina. So you load on the machine, and then it does the sequencing for you, depending on which technology. Each of this sequencing has different technology. What I mean by technology, different, probably like the dyes and different pattern in which, their reads are called. And then the next step is the step 4, where you do the analysis. I'll just give us a brief workflow. So for those of you that are going to be in the dry lab, probably developing pipelines and all of that. So after those in the wet lab will get to do, and then those in the dry lab. But it doesn't mean that while you're in the wet lab doesn't mean you can't do in the dry lab, right? So in the step 4 is where you analyze the data using a cocktail of different tools, right? Which would involve cleaning the reads if the sequencing was not, didn't turn out fine, and then removing adapters. If you see that in step 2, that's I think the blue color there, which are called the adapters that are tagged at the 2 ends, both the left and the right of the red and the purple, right? So during analysis, you have to remove those adapters so that you would have the insert, which is the DNA fragment shown in step 2, right? And that's the focus. The adapters, in most cases, like most of them contains known region or known DNA or conserved DNA that have been known, which are tagged, such that the sequencing will start from the known and then gets to the unknown, which are your fragment, and then amplifies everything. These techniques have been used in discovery of novel viruses, novel bacteria, and other pathogens, right? So that's just a quick summary. Please, if I'm too fast, just tell me to slow down, right? Am I too fast?
No, sir.
All right.
Just to be sure that I'm not talking to myself. Can anybody hear me?
Yes.
Yes, sir. We can hear you, sir.
Yes, sir, we
we
can hear
can.
you.
Yes,
Please
I can hear
slow.
you, sir.
Can you hear us, Dr. George? Can anyone else hear him? I think
Yes,
I
sir.
think his network is
I think we lost Dr. George, but
yes, I think
yeah,
his network fluctuated for a bit there.
yeah.
Hopefully he joins us back soon. You can just hang on till he joins us back. Stretch your legs, stand up, and if you are sitting down in the meantime, and move a bit around before he joins back. Yeah, we also support LD online meetings. I hope you have stood up where you're sitting and you stretch your legs. Dr. George is trying to join in. He still has issues with his network. But please and please don't just take this as just a say. Please actually stand up and move around. I believe you'll be sitting for a while. So you can also stand up and listen as we move on. I think Dr. George has resumed. Okay, you can take it from there. Please help us spotlight him. Thank you very much.
Okay, thank you. Apologies. Sorry, I was knocked out by the internet here, so I had to switch to a different network. So who can just remind us where were we, so I can know where to start? Where did we cut off? Where were we knocked off?
Okay, you were in the
Oh, I was
second
just talking
stage
to
of
myself
the
all through.
explanation. So you were
Okay,
explaining the
did I show
second
the, did you see the
phase.
picture about the summary? Oh, great.
Yes, yes.
Great.
Yeah, so you
Okay.
were explaining the blue color in the
Okay, let me
DNA strand
just,
of the second stage.
okay. I guess after that I was talking to myself all through. So let me quickly share again and then we just proceed from there. Great. Okay, so we'll share this again. Good. So is this where we were before the internet disruption?
Yes, sir.
Yes. Great, perfect. So please so we're gonna be interacting so that I know I'm not talking to myself. Network is really terrible in Nigeria. Though Nigeria is a great country, but hopefully things will get better. So as I was mentioning, so I'll just recap the whole workflow again, right? So I mentioned probably this doesn't need to be DNA. So it could be RNA extraction in step 1. So depending on what your starting material is, depending on your research objective, right? So if your objective is, oh, I want to do it transcriptomics, or does transcript means probably targeting ribosomal RNA, messenger RNA, right? So your starting material could be RNA. But in that case, you have to convert the RNA to complementary DNA, which is called cDNA. If your objective is targeting DNA, like the Human Genome Project, so in that case, your extraction is going to be DNA. Okay, so that you don't always think it's DNA all through, right? But the different sequencing technology only recognizes DNA. So you need to convert the RNA, if your starting material is RNA, to DNA. And then in step 2 is where, after probably converting your RNA to cDNA, which is a complementary DNA, or you started with the DNA, you're going to fragment this DNA, right, using different enzymes, which during the course of this study, we're going to have a detailed information on that. So it's these fragments that you add adapters. Adapters are like unique in sequences, right, that have known region, known sequences, since you don't know your own DNA fragment. So what is done is that you tag this unknown sequences with the known, such that the sequencing will start with the known, for example, ATTGGG, right? You could start reading from A and then add a T, A add a T, G add a C, and then you have a starting material until it gets to your sequences, which in this case are the red color and the pink color in the middle. Sequences that and then gets back to the light blue, if I'm not mistaken, right? Which are the adapters at the 5' end and the 3' end, flanking, the different ends. So after you've done that, your library is ready. You go to step 3, which is the sequencing platform. Like I mentioned, there are different sequencing platform. So depending on the sequencing platform, but for IGH, we have all the sequencing platform. So during the course of the training, probably, or for those of you that would come to IGH here, you also have the privilege to see all the sequencing platform in real time, not just virtual here, right? So that you have the background knowledge on, what the sequencing platforms are and so on, right? So in step 3, depending on which platform you're actually working from, could be ONT, Oxford Nanopore Technology, could be Ion Torrent, could be Illumina, it could be PacBio, right? Depending on which of those platforms, you load your library, and then it's gonna do the sequencing run for you. Okay, and then after the sequencing in step 4, Like I mentioned, for those of you in the wet lab, dry lab, you should also have a knowledge on how to analyze your data, right? Because it helps you track what went wrong during the sequencing stage. So whether you're a wet lab person, I would also encourage you to also have a background knowledge of data analysis of your samples. So in step 4 here, there are different processes which are, put into play. The first thing you'd want to do is, remember in step 2, you added the adapters, right? So the very first thing you want to do is remove the adapters, because the adapters are not part of the red and purple fragment. And if you allow the adapter stay, it's going to bias the outcome of your analysis, whether it's genomics, transcriptomics, or whatever, downstream analysis your research question was focusing. So we always remove adapter, and in most cases, depending on the sequencing run, which I'm not going to go into detail. So with your FASTQ files, you could use a tool called, with your FASTQ file, there's a tool called FastQC. Okay, so with FastQC, you could check the quality of the run to see if the run went well, if you have maybe insertions, poor sequences, and all of that. And when you have that, what you do is you trim again to remove those poor regions. So that's part of what you do in your analysis. You align the read. After that, you align the read to get your BAM file. You identify variants, that's called variant calling, depending on the workflow. And then you can go downstream to do other analysis. So I'll just move quickly. So this is just a summary of what I mentioned earlier. So in the sample preparation, this could be your DNA or RNA extraction, right? And then during library preparation, you have fragmentation, adapter ligation, then PCR just to amplify. This is optional, right? And then the sequencing, this could be platform specific, and chemistry. When I mean chemistry, there are different dyes, there are different technologies that differentiate Oxford nanopore sequencing from Illumina sequencing. Remember I mentioned earlier when I said one is long read, based on the long read sequencing, the other one is based on short fragmented read sequencing. So depending on each of the platform and depending on the finances, all these platforms are a bit very expensive, but there are some that are cheaper to get, like ONT, Ion Torrents, and all of that. They're a bit cheaper than the PacBio and the Illumina sequencing. So depending on which technology, you're going to generate short reads or long reads, right? So after you generate that, you go to the next phase, which is the bioinformatic analysis, right? And then that's where you do your base calling. So base calling is simply converting the raw signal that you get from sequencing into your nucleotide sequencing. I don't know, have you been taught about the different nucleotide sequence bases? Have you been taught about different nucleotide? Do you know about the ATG, right?
Yes,
During
sir.
the course of this training, have you heard about that?
Yes,
Your
sir.
thymine
Yes,
and
sir.
thymidine and all of that. Good. So what the base calling simply involves is it converts this raw signal into ATGs depending on the starting material you use, right? That's all it does. And then I mentioned about the quality control. So you assess the quality of control using FastQC. Another thing you do during quality control is you remove adapter. And then what you do, which is very important now, if you're working with the human genome, one of the most important things you want to do is remove the host read. So there's this ethical issue which we have with the Human Genome Project that, so if you're sequencing a virus, you're trying to find a virus from probably human samples and all of that, you don't just submit all the raw sequences. So what you do, you need to remove the human host, depletes the host. If you submit it like that, everything with the host, it's unethical because somebody could go use those data set to track whoever the person was, right? So those are some ethical things that we remove the host. And apart from that, removing another issue about host removal is most time the hosts tend to mask the pathogen of interest, probably bacterial virus that you're sequencing, and may not allow you get maybe a good coverage of the genome. So you also take that into control during quality control, especially for those of you who are going to be working on the bioinformatics section, right? So these are some of the things you do before you go downstream in your analysis. It is very, very important that you take all of these things into consideration. And then after you're done with that, you're going to have to go through a two-way assembly. So we have what we call the reference-based assembly, and we also have what we call the de novo assembly. So in case of the reference-based assembly, it simply involves you, for example, HIV, you go to the database and pick probably HIV-1, reference sequence of HIV-1 that have already been deposited in the NCBI database. And maybe you were working on sequencing HIV among, HIV infected cohort. So after your run is finished, you simply map your raw reads after you've depleted of host and then done your quality check, remove adapter. You map the raw reads to the reference you retrieve from the NCBI database. And then you check how much of the read were able to align with the reference to give you a genome. That is what we do with reference-based assembly. The other assembly is de novo, means you're not providing any reference, but you're simply telling the algorithm, go to the database. There's also, it uses the de Broglie principle and also based on the KMA size. So what it does is that it's an algorithm that goes into the database and try to look out for sequences that aligns to itself based on that virus and assemble de novo without using any reference. Okay, there's also a tool, there are different assemblers that does that, including Spades, MetaSpades, you have MegaHit, there are different tools that do all of that. So depending on your research question, you could tilt towards reference-based assembly or you could tilt towards de novo assembly. And then there's also a way where you can do reference-based de novo assembly, right? Such that you have a guide, you've already done your de novo assembly, you still map whatever thing based on that reference, just so further gives you a high level of reliability. Some people have seen that reference-based guided de novo assembly seem to give a higher reliability compared to just de novo assembly. So after you're done with all of that, the next thing you do is annotation and probably your downstream analysis. I also said, depending on your research question, okay, your research question could stop at, oh, you have found the virus, you annotated that maybe it is a particular type of HIV subtype, maybe HIV subtype M or subtype D or subtype, any of the subtype. You could stop there. The next thing you might want to do in your downstream analysis is, oh, what are the single nucleotide polymorphisms or the changes you found in your genome that were different from the reference genome? What are those changes likely markers for infectivity? Are they markers for maybe the virus adaptation? Sorry, I'm tilting towards virus because I'm a virologist. I work in viruses. But for those of you who are working on cancer, right? So let's assume you were sequencing the human genome, maybe telomeres, or depending on the particular region, maybe you found a sample that was suspecting of cancer, right? So you were sequencing that, probably the full genome, to see if there were changes in that genome that could be like markers for maybe cancer, or you were doing like transcriptomics, depending on your workflow, what your research question was. And then in the case of transcriptomics, you want to see different genes that are upregulated with the cancer infected cell and the uninfected cell. So you compare the controls and then you see, oh, what are the patterns in your sequencing that you could give a guide. So those are some of the things that, sorry, are we still together? Just to be sure my screen is hanging.
Yes, sir.
Yes, sir. We're with you, sir.
Sorry. So let me stop and share again. My screen is actually hanging. Great. Sorry, just a jiffy, and then. Okay, so I think it's working now. So I'll share again. Okay. Great. So can you all see my screen?
Yes, sir.
Great. So I'm trying to. Good. Okay. So The next thing is application of NGS, next generation sequencing. So next generation sequencing has a wide range of application. If you're looking at the whole genome sequencing, so in this case, you want to sequence the entire genome of a human, you want to sequence the entire genome of a goat, or entire genome of a bacteria or virus, right? So this is what we mean by the whole genome sequencing, just like what started with Sanger sequence, the Human Genome Project using Sanger sequencing. But now it's easier. I mean, Dio, how long did it take to sequence when the PacBio arrived? I think it took like a couple of days that we had the first human whole genome sequencing done, at IGH. I think it took a couple of days compared to, what took with Sanger sequencing a couple of years, right? To get the Human Genome Project ongoing. Yeah. And then we also have the whole exome sequencing, right? So exome, what I mean by exome, you're looking at regions that code for a particular protein. So we have come to realize that in the Human Genome Project, out of the, I think, 3.4 billion base pair, right? 3 billion, over 3 billion base pair. Only a few region, a few percentage of the genome actually coded for protein. The other region, a high proportion of, I think, over 60% or thereabout, if I'm not mistaken, were like coding for non-translated sequences. It doesn't mean that they are nonsense region. They also play a role in expression, gene expression, transcription, and all of that. But they weren't coding for any protein. So researchers, agree that instead of just wasting your time sequencing everything, why can't we just focus on the region that codes for maybe protein, right? So they design different assays to focus on that region and then just sequence only the protein coding region. So that's where you have the whole exome sequencing. And then you also have the RNA-seq for transcriptome profiling. So in this case, you want to observe, like I mentioned earlier, the cancer, for those of you that are into cancer or precision medicine. You want to see, maybe you've had a case control study, and in this case control study, you have a cohort that were exposed to a particular chemical, right? Maybe people ultraviolet rays, or they were exposed to maybe inhaling a particular substance that it kind of changes that led to cancer. So what you want to do is, you want to collect this cohort and healthy group, do a gene expression, what genes are expressed in them that are, when I mean expressed, are upregulated or downregulated. For example, in cancer genes, there are different markers like P53, which is like a restriction, it restricts proliferation of cells, during cell growth and all of that. It tends to, they are called tumor suppressor genes rather. So when you see an expression of this gene, you can tell what is going on. That a gene that is supposed to be downregulated is upregulated, meaning that something is wrong. So in this case of RNA-seq, you could look for those profiles. Among these cohorts that have the cancer, which genes are being expressed. So it gives you an insight, especially for those that are interested in precision medicine, to have a better understanding of what is really happening among those cohorts, right? And then you also have the metagenomics sequencing. So what this does is that in the case of metagenomics, you want to have an insight of, for example, you collected samples from the environment, or maybe you collected sample from the sea, maybe Lagos River. Sorry, is it the Lagos River? Lagos, the big IC. So Lagos is like an island, so you have so many waters around. So maybe you collected from Lekki Beach, you collected from Bar Beach, all those beaches, and then you want to check what are the different organisms that are present in this water body. Are they likely pathogenic organisms? And so those could be your research questions. So in this case, you don't really have a preference for any particular pathogen, but you want to see the complete profile of the microbial community that are in those samples. So you can do that with next generation sequencing. And then you also have the ChIP-seq for DNA protein methyl. So in this case, the target is actually the methylation sequences. This is mostly used for epigenetic profiling. For those of us that want to go deeper, and then apart from the fact that next generation sequences has this high throughput turnaround, has this massive benefit, they are also challenges with or limitation with next generation sequencing. But I'll start first with the advantages. Like, ever since the introduction of next generation sequencing, I mean, compared to Sanger sequencing that took almost like ages to finish the human genome, within 4 to 5 days, we were able to sequence a full human genome instead of taking years. Okay, so the short turnaround time, the faster sequencing, those are some of the strength, and then the massive data, like I mentioned about the metagenomics, unlike Sanger sequencing where you just target a particular region per time. In the case of metagenomic using next generation sequencing, you could have tons or millions of pathogens, detected in one single run. So you have massive data output, multiplexing and then next generation have also helped us discover rare variants, like the case of SARS-CoV-2. When the outbreak first came, the first genome that was gotten from Wuhan, from China, they used next generation sequencing platform. Within a couple of days, they were able to see that this was a different variant from SARS-CoV, the first SARS coronavirus that was detected in 2003. Right? And that was why they were able to get vaccine in short time. It takes 10 to 15 years to produce one vaccine. But because of, the technology development, we were able to get all of those things done. And without the genome of that virus, there's no way vaccine would have come. There's no way diagnostic kits would have been produced. So those are some of the advantages. But limitation is that, when you have massive data generated, we also need high level, computational tool to be able to use this data. And this is where Africa is trying to position itself. Although Africa is still struggling, but gradually, I mean, there are some centers in Africa that are beginning to take this as a task that is achievable, right? So this massive turnout of data also means that, you need high data storage, high computational power. And then there's these challenges with short read sequencing compared to long read, which is also problematic. And then some of the sequencing, next generation sequencing platform does not come cheap. Maybe, I don't know if Ogadayo had told you guys the cost of buying one pack bio now, or the cost of buying a Novasec X. Some of these equipments still cost in the range of hundreds of thousands of dollars, right? If not million. Novasec X is like almost 1 million USD. So these equipments are still very expensive, right? And some countries in Africa are battling, to solve their own economic woes, and very few are willing to, invest in this technology. But I'm thankful for the few countries, the few centers that have been able, to take up these challenges and to see how they could reposition Africa so they could, benefit from this unique development in next generation sequencing. Right, so those are just few of the limitation, and then this is just example of the pipeline I mentioned to you in the step 4, which includes your sample DNA extract. This is just a workflow of the whole thing: sample preparation, DNA extraction, library prep, sequencing, fast QC output, quality control, host reads removal. Just a summary, reference mapping, and then annotation and visualization. So that's just a short introduction I'm giving to us. So I'm going to keep the floor to questions so I don't really overflock myself and repeat myself like an OCRAC CD. And if I was too fast, please, this is your time to take time, ask questions. If you need more clarity, I'm happy Dr. Ogadayo is still here. What I can answer, he would also chip in, to provide more clarity. So I'm open to more questions and answers. And I'm going to be calling your name randomly just to show if you are following us, to ask questions if you don't have questions. So the floor is open now for questions. Yeah, over to everyone. I guess I can stop sharing now. So I'm going to stop sharing so I can see all the names here, and I might be calling you by your names if you don't have questions. So just, if you need more clarity, just, pop up. Okay, so that's the first question here. So I'll just read. So is there a criteria to select NGS platform to be used specifically? Well, that's a very, very good and interesting question. There is no criteria. especially working in a resource-limited environment. Like, well, Africa is not resource-limited. Let me not use that word because God has blessed us so much. So working in an area where this technology is not well developed, right? So you're going to have to consider two things. Like I mentioned, the sequencing platform are a bit very expensive, and not every university, especially in Nigeria, to be precise, can afford some of this sequencing technology. So most times you could start with what you have. So if you have the cheaper options like the ONT and the rest, you could start with that. Okay, so it's just like a game of all your pockets. And then it also depends on your research question. So if your target is short read, short read sequencing and all of that, then the best option would be to go for Illumina sequencing. So if you're tilted towards a long read, right, the best option is PacBio, but the cheapest option would be ONT and Ion Torrent and the rest, but those are all the options. So first you have to consider your research question. What is your research interest? And then you have to consider your pocket. How much can the money I have, afford, be able to answer some of my research questions? So those are two things you have to consider before you select a platform. And then if you're interested in short read sequencing with higher depth, then Illumina platform will give you that. If you want a long read with high quality, high fidelity and all of that in sequencing, then PacBio is the first choice. I don't know if I've been able to answer your question. Dio, do you want to chip in something there?
I think you've summarized that it is dependent on your research goal. So, but yeah, depending on your research goal, you just need to evaluate the sequencing technology. And like Dr. George said, it's also dependent on the available resources that you have. However, the research dynamics and productivity changes over time. So you also need to keep in tandem with the state-of-the-art conduct of research so that you know how to churn out adequate data. Every research technology, every genomic technology has their limitations. So, but these limitations can only be overcome when you have a plethora or you have access to a plethora of equipment. But if you have limited access, you just need to make do with what you have. That's all.
Thank you so very much, Dio. I think Damilare Taiwo's hand was up. Damilare, I hope you're not shy. Just feel free. It's a free world, and here we don't eat anybody, okay? Yeah,
Yes.
go ahead, please.
Thank you, sir. I'm just during your presentation, I'm just trying to think around the world of science currently, because now, if you collect a sample, you want to identify maybe biochemical test, morphological test, but now you just move straight to sequencing. You might decide not to do any kind of molecular work anymore, just sequence, and then you will know what you're looking for. But then I have this question that if we are taking our sample straight down to sequencing, and what is going to happen to the molecular biology skills in use basically because very soon now, just get your sample and sequence, either metagenomics or transcriptomics or whole genome sequence. Once you have your sample, just sequence. You will know during your base calling and know about the bioinformatics. You can identify probably a particular gene in mutation you are looking for straight there. But I'm just being curious, like, is it that the molecular biology skills is becoming obsolete, no longer prioritized in the lab? Because right now, everybody just want to do NGS. Everybody want to do metagenomics. And there is no, okay, let me run PCR, let me check gel, let me do this. Do I need to optimize my protocol? But we see in most research or manuscripts that they just want to see the result of your sequencing. What is the outcome of everything you've done in the lab? I just want you to I don't know.
Great, that's a very, very interesting question. So I would go back to the case of SARS-CoV-2. Molecular biology techniques are not going to be absolute, not now, not in the next 20, 30 years, right? So when SARS-CoV-2 was first reported, I think December 2019, so the guys in the Wuhan Institute of Virology and the Chinese Academy of Sciences, were able to report the genome. They did metagenomic sequencing because first, you can't report what you don't know. So for them to determine what was there, so they needed to use next generation sequencing, which is able, remember I told you about fragmenting your DNA sequence and then adding adapters.
Yes, yes, sir.
You can't do that with the conventional tools, right?
Yes, yes,
So
yes, sir.
for them to really know what was there without giving a false report, so they had to use NGS sequencing tool. After they got the genome, they knew, oh, this was a virus that was different from what was reported in 2003. They now designed PCR. Immediately they submitted their genome in GenBank. Almost the whole lab in the whole world was able to use their sequence to design PCR.
Okay.
And with that, they went back to the lab to start testing how many people were actually positive. So because you have NGS does not mean others go out. It's a complementary, it's just to complement every aspect of molecular assay. So because they found the whole genome, they were able to design PCR to screen. They were able to design ELISA, with that they could get the antigen, the spike, the different region to design ELISA. Even those in immunology also benefited. So it's like to complement other aspects of molecular biology.
Okay.
Not really to compete. So with that, that's why all of us were tested for PCR on SARS-CoV-2. But if you don't know the sequence, how do you do that? So it's just a way to complement other aspects of molecular biology. And then going back to bacteria, it's also, it doesn't mean you don't still run those are classical techniques that you run your biochemical tests. The only thing is that you don't need to run PCR to screen for the different resistant genes because you're going to get all of that in your whole genome.
Yes, yes, sir.
If you're targeting bacteria.
Yes, sir.
So it's a way to complement. And then there are some journals that would insist you go back to run PCR to validate that bacteria or virus that you isolated using next generation sequencing. Journals like Nature, journals like all the top journals will always insist, did you do PCR to validate that? Some of them do that, right?
Yes, yes,
So it
yes.
doesn't mean that, NGS is like a magic bullet that solves all the problem in the world. No.
No, I've just been curious actually, sir, because I know that molecular biology techniques is just like if you don't even just sequence and have everything you're looking for in an isolate, you can have the gene of your interest. Thank you so much, sir, for that presentation. Thank you, sir.
No, it's only to guide. So with that gene now, you can now go and then play around and then do more in-depth work. So it's only to give you that sequence. I don't know if I've been able to clarify on that. So it's not a magic bullet. It doesn't answer all the questions. It's only to complement other aspects. So there's another question here. I think I'll take Ayomide Jegede. So he's saying, so cost, research questions, and availability of results are key factors to consider. Okay, just like telling us more. Yes, so you need to consider the cost. Cost in the sense that I always tell us, start small. You don't need to start with the Illumina PacBio. If God has blessed your lab or wherever you are with Oxford Nanopore technology, which is a bit cheaper and simpler to run, you could start with that. Like, biblically, Moses in the Bible was told, what do you have in your hand? He had just rod, and that's what he used to part the Red Sea. So most time God will ask you that. What do you have? If you have ONT, maximize that. If you have Illumina, maximize that. If you have PacBio that God has blessed, like IGH has all the platforms, it's a blessing. But you don't, some of the institutions, you don't compete. So whatever you have, start from there, and then, it's the data you generate over time that you can now, that's how IGH started. ACEGID back then had just MySeq. It was a MySeq that they were able to sequence the 2014 Ebola, samples that, Nigeria, that saved Nigeria from the worst case scenario. And with that, that was how the center, and then when SARS-CoV-2 came, we still you had the same MySeq. Other platform had not come yet. And IGH were the first in the whole of Africa to sequence the first case of SARS-CoV-2 from the patient, Italian that came to Nigeria. And immediately they were able to submit that. And that was the transformation, where the turning point came. And today, I can boldly say IGH has all Any platform you mention, you're going to find it here. For those of you who will be privileged to come down, okay, and do the lab tour, you're going to see all of those things. So you start with what you have, okay? And then the next, can you briefly talk more on next generation sequencing and Sanger again, and what application are these two most explored? Practical cases. Okay, so this is a very good question from Aniola Alex. Oh, very good. So next generation sequencing is just a little bit upgrade from Sanger sequencing. Okay, depending on the dye, but the only advantage is that with the case of next generation sequencing, the turnaround time is reduced, unlike the case of Sanger sequencing, which is a bit very laborious. And then with Sanger sequencing, I would say Sanger sequencing is still the gold standard in terms of error rates. It has fewer error rates compared to some of the next generation sequencing platform. That's why some labs, would still have to confirm with Sanger sequencing whatever thing you've generated from other next generation sequencing platform, right? It's still the gold standard in terms of error rate. So for your next generation sequencing, I mentioned in the application, there are so many applications of next generation sequencing. So practically, I'll always use the case of cancer. If you want to check for gene expression, maybe do a gene precision medicine, right? In this case, you want to track for cells that are transformed, cancerous cells. Maybe you got papilloma, someone infected with human papillomavirus, maybe you got the pustule or you got the infected cell, and you want to see, based on this cohort that have this infected cell, what is really wrong with that cell. So you can sequence that cell, or you get their blood, get PBMC, and then from the PBMCs, the cells, you can check how the cells are expressed compared to the healthy people that don't have that symptom. So those are some of the cases that NGS can help you. You could check probably like the cancer suppressor cells. Are they actually increasing in number, or they are reducing in number? So that gives you a guide. If they're increasing in number, it means something is making them transform. If they are reducing in number, which you should find in the healthy cohort, it means the system is normal and they are not, there's so much pressure that they are undergoing, which will make them, get overexpressed. So those are little things you can get from NGS. Well, however, in the case of Sanger sequencing, you can still achieve the same thing, but in a limited way, such that for Sanger sequencing, you might not be, I think, sorry, you can achieve that using qPCR, sorry. It's a qPCR that you can check the gene expression and all of that. But for Sanger sequencing, if you're looking at short reads, maybe you're targeting different genes, maybe in an infected cohort, you want to target those genes and sequence the gene just to see if they have these mutated genes. You can use, Sanger sequencing to answer some of those questions. I don't know if I've been able to answer your question in your lab. And then just quickly running, I think we're behind time. Olanrewaju Osika. Say thank you very much for the insight. Are there any disadvantages to multiplexing of different samples? Are there disadvantages? So when we say multiplexing, yeah, I wish you could specify here. So there are some cases where, because of lack of cost, okay, for example, you collected samples from 3 locations outside. For example, you collected sample from Lagos in Nigeria, maybe from dogs in Lagos, you collected samples from Abuja, dogs from Abuja, and you collected sample from dogs in Osun State. But because you don't have money to sequence each of the dog sample from Abuja, dog sample from Lagos, dog sample from Osun State, you can pull the samples. When I mean pulling, not pulling in terms of the library, okay? So because you don't have money to single sequence individual sample, you can pull the sample into one and sequence. In this case, you just want to do a qualitative analysis to see what are present across dogs from different regions in Nigeria. However, there's a limitation in that case, because here you will not be able to know the true microbial diversity in dogs from Lagos. You will not be able to know the true diversity of microbial diversity in dogs from Abuja, or the diversity of dogs from Osun State. So that limits your level of interpretation of the data per time. But if you have the funds, you could sequence the dog sample from Lagos, dog sample from probably Abuja, and dog sample from Osun State. Maybe in this case, those dogs were infected with rabies. So you want to see dog infected with rabies and what is their gene expression pattern like? Are they upregulated dog? And then you compare that with maybe controls you got from those samples. You have a better picture to like say, oh, when you see dogs in any region of Nigeria or globally, this is the pattern of gene expression you want to see. Or when you see dogs infected with rabies, these are the kind of lineages that are circulating in maybe Lagos, in Abuja, and so on. So there's a limitation to multiplexing. And then depending on multiplexing, maybe you're pulling samples in during library preparation. So at the stage of sample pooling, there's also a limit to the number of pools. So you need to do your concentration, your library concentration to know what number of samples you can pool so that you can have coverage, better coverage for that genome. I don't know if I've been able to provide clarity on that, Olanrewaju. And then Samson Okwemi says, for a bacterial isolate with the aim of identifying the bacteria to its species level, do you suggest whole genome sequencing or not? Very interesting. So if you want to do bacterial identification to the species level, I would always say go with the whole genome sequencing, because it will give you, so at that level, you're going to have a detailed information of the different bacteria. And just to bring this to notification, the classical technique of culturing bacteria and telling it by their morphology is very limiting. A study we did on bacteria in bats, and also, we were able to find, so we observed that what we had in the culture, so we had these staph aureus, staph aureus that had the same morphology like staph, and had the same characteristics. But when we did the whole genome sequencing, we saw that there were slight differences from the reference staph, that we found, that there were other species members. We found staph gallinarium, we found other subtype in the staph complex. And then the interesting thing is that some of these bacteria might be existing in a complex, but the morphology will tell you, oh, is this species? So to really clarify that, whole genome sequencing will give you the complete genome of, whatever bacteria species that you're looking for. And then you can now use that as a guide to go back to cell culture to see what went wrong during maybe the biochemical test or during the initial PCR test that you ran, right? So those are some of the advantages of whole genome sequencing. And then Adekunle Showole said, for the whole genome sequencing method, I want to know what is going to be used to extract the portion of interest on the genome. A very interesting question. So after sequencing, remember you have your adapters tagged at the 5' and the 3' end. So what you do is, there are different tools that we use to extract. First thing is you delete or remove the adapter. So you could do that using tools like FastP. You could use that using tools like Trimomatic. So in the case of Trimomatic, which I use regularly, it's an algorithm that goes into your sequence, and based on the adapter sequences, there are universal adapter sequences that are like in the database that are curated. It's like a library of adapters. So it's the tool Trimomatic uses this, and then it removes the adapter and allows only your insert DNA that was sequenced to exist. And after you've gotten your insert, you've removed the adapters and other poor sequences using Trimomatic. You now use assemblers. I told you could do what we call reference-based assembly, or you could do what we call de novo assembly. So in the case of de novo assembly, there are different tools. You could use spades, you could use meta spades, you could use mega hits, right? There are different assemblers that could help you, assemble a portion of your genome of interest after sequencing. Yeah, so I hope I've been able to answer your question. We're already 1 o'clock. I'm supposed to jump out by 1, but I'm going to take a few more. So let's see. Oneseta Nebonoses. I hope I pronounced your name well. Please pardon me if I murdered your name. So thank you very much, sir. Firstly, what's the difference between short and long reads? I'm not sure if you've already talked about it. And secondly, is there preference to anyone, or it just depends on what you want to use it for? Maybe I should allow Dr. Dayo answer this. Chief Dayo, are you still in? Do you want to take that?
Yes. Currently,
Yeah, please go ahead,
the
sir.
short read sequences are the most commonly used and widely acceptable. The long read sequences have not hit their perfection mark. So I see a future maybe in the where long read sequences are going to be used more compared to the short read. Take for example, the Illumina sequencer is the most popular short read sequencing technology used. And one of the limitations is that when you have repeated the parts of the genome, those are parts of the genome that you have, maybe A is all true, T is all true, or AT and all of those things. It tends to make mistake as the enzyme might slip off the strand and might not sequence it properly. But long read sequences can overcome that. But they are still subject to errors. And some of those errors are limitations that they're overcoming. Also, there's also the place of marketing in these technologies. If the new technology can market their products will perfect it and get more people to use it, then you will see them in use. So, but that's that.
Great. Yeah, great. So I think just to add to what that you have said, so it's a technology for the long read and the short read. So they have been able to base their algorithm based on, like the case of Illumina, where you fragment this short reads, and then during sequencing, you have like sequences, short sequences that are generated, and then these sequences are like like in a ladder, mapped, right, thousands of times, where you have the depth, and then AA, you find like the region that are mapped over time, you find AAAA, you find TTTT, just like that. So there are different technologies, right? I think during the course of this training, for those of you too that are going to come in, we're going to give you detailed information on that. Just to quickly jump, Fanny Olakunle said, what do you advise on where to start to study and gain skills for the dry lab aspect concerning genome sequencing? Yeah, very, very interesting question. So for those of you that are tilted into the dry lab, maybe you want to be a bioinformatics only or probably data analysis. Yeah. So you could start with, I always say, I mean, YouTube is a place where you have tons of videos, right? Where you could get so much of this. But one of the easiest starting points would be the Welcome Genome. There's this Welcome Genome course, which is online. So you could go there. They have this bioinformatics for beginners, where you learn what FASTQ is, how to clean your FASTQ. So you could look that up. Probably, I don't know if I can get a link before the end of this session just to share with us, right? Please remind me before the end of this. Remind me before the end of this session. I would try and share the link to us, right? So that would be a good starting point. That would be a good starting point. Sorry, I have a background here. And then the next question is, can NGS be done without the adapters? Is that a possibility, or it is an essential as primers? It is an essential as primers. So if you want to start from the known to the unknown, so you need the adapters. Remember during the course of the presentation, which I showed in step 2, so the adapter is like the known, which you want to move, like your PCR, you want to move to the known to the, from the known to the unknown. So you need the adapters tapped so that you could, you know, unambiguously run the sequencing run. So yes, it's as essential as the primers. And then Kelechi Manuela says, please, can there be errors when sequencing? And please, how can they be corrected or avoided? Definitely, there are tons of errors while sequencing. So the sequencing could come during library preparation, where you have probably contamination that we included during your library, right? And at the end, you amplify, for example, your lab, if your lab is known for sequencing SARS-CoV-2 or monkeypox, and then you're working on samples that came from, let's say these samples came from rodents, right? and then you're finding monkeypox in rodents. It looks a bit, it's possible that there could be monkeypox in rodents. I don't know which other example I could cite, but then you need to do a quality check to be sure that it wasn't lab contaminated, right? So these are things you expect. And then in sometimes too, you could have during the sequencing run, you have probably in the course of this training, they're going to show you poor data and good sequencing data. So when you have that, you're going to see that some of the sequences are very poor at the maybe 3' end after the run. So what you do there, you could have to keep trimming those bad sequences off. Another error that could come is when you allow your adapters, you don't remove your adapters and you go downstream the analysis. And then the adapters become part of your genome. That could give a false, maybe insertion or deletion, and could maybe misdirect the scientific community. Yes, so definitely there's so many errors that could come up here. So some could be self-error, could be multiple errors. So concerning the host read removal on the workflow, which tool is used or enzyme? So what we do during the host, so during sequences or prior to library preparation, you could have what we call host depletion. It's what we do regularly in the lab where you deplete the host. In this case, you want to remove the ribosomal RNA. You want to, they say, so you can run some assay using 18S. So we do that regularly in a lab. So you could use that to target the host and deplete that. And then after sequencing, which is what is recommended. So there is a bioinformatics tool that you could use to deplete the host. In this case, you could map, the easiest one is map the host using a tool called Bowtie. So you map the host. Sorry, I think my time is up, guys, right? So you map the host to, you map your reads to the host. In this case, if you're working on humans, you could map all the reads you've generated from the sequencing to the human reference genome. So the reads for human genome will be highlighted, and the reads not mapping to human genome will be highlighted. The reads not mapping to human genome is your reads of interest. So what you do, you just extract that from the BAM file and use for your downstream analysis. So that's what we do. So we suggest you do that during library preparation and after library preparation. But the point is that it's usually difficult during library preparation because it's time consuming. So most people just after sequencing, they use bioinformatics tool to like handle that. Yeah, and then I'm gonna take the last question here from Moses Ukwaja. I hope I pronounce your name well. So when comparing next generation sequencing versus quantitative PCR technology, what could be the key difference? Yes, so one of the key difference when comparing next generation sequencing quantitatively, especially during gene expression and then PCR expression, is that you're going to find novel transcripts. So depending on which transcriptomic analysis you're doing, if you're doing bulk RNA sequencing or you're doing single cell RNA sequencing, irrespective of that, in bulk, you're going to find both bulk and single cell, you're going to find novel, when I mean novel transcript, you're going to find novel gene expression patterns. Unlike PCR, where you're only targeting previously described genes. So there's a limitation there. In PCR, you can only target previously described genes that have been previously reported, depending on that pathogen or the host that you're working with. But in the case of NGS, you're going to find novel transcript, novel genes that have not been reported before using the sequencing technology. So those are the key advantages. And apart from finding novel gene, you're also going to find previously reported gene expression pattern. So those are the strength of NGS, right? And also, microarray and all of that. Yeah, so I think I would want to hand over to the IT guys now. I think I've been able to answer all the questions.
All right, thank you very much.
Yeah. Okay, thank you so very much. Yeah.
Okay, you can take some Okoyemi. You can take some Okoyemi.
Okay. So Okoyemi,
Yeah,
please
good
go
morning,
ahead.
sir. Thank you for the wonderful presentation, sir.
I am actually the one that asked the question about the bacterial profiling the other time. Why I was bothered a little bit was the fact that I'm currently working on my master's degree in OAU Ife. And during the first laboratory test, we did the biochemical, and by that is able to produce means the green pigmentation should definitely be Pseudomonas aeruginosa. So we now compiled a list of about 20 of those bacteria sample, and after carrying out the NGS, none of them actually come out to be Pseudomonas. None of them were there. So I was a little bit confused. So I was, when you now said NGS should at least complementary, you said it's not out there to totally eradicate the PCR and some of the biochemical tests we run in the laboratory. So again, I'm going for another sequencing now. To some extent, I'm afraid because I don't want to waste more money. And my organism of interest is actually Pseudomonas aeruginosa and maybe Bacillus because I'm working on soil sample. So after running the biochemical test now, what do you think I can do? Because at this extent now, I'm being skeptical about what to do next. Because I know for sure as a microbiologist, once I'm able to run some biochemical tests in the lab, maybe in terms of pigmentation production from this bacteria, this is the bacteria. Now, running the NGS, I was shocked. None of them, none out of the 20, none. So
I agree. We've had that experience before. So you know Professor Shitu, right? In OAUs, yeah. So
yes, sir.
So we've done a couple of work with him in his lab. So in some cases, you could have what we call mixed isolate. So what you have, your case might not be a classical case of E. coli or something, which depending on. So if you check, there could be like a mixed isolate there. So most time when you sequence, that's what you find. We had a PhD student in our center here who reported that in fact she repeated her sequencing like 2-3 times and still found the same consistent result. So I think what she got there was she was working on some salmonella. She was looking at salmonella, but she got the culture right, but sequencing was not salmonella. So like
it is always, sir.
I said, classical microbiology needs to be a rebranding and repackaging of so many things, right?
I agree, sir.
There need to be a repackaging. Some of the morphology we claim, there are so many things that need to be updated that have not yet been updated. So next generation sequencing or whole genome sequencing of those bacterial isolates is now giving us a new pattern to see that some of these techniques needs to be upgraded. So those are some of the advantages too that, you know, comes in. So what you can do, depending on what you get, you can design new primers, you know, to go back and screen your other isolates, and then probably you might be surprised at what you get. Is that okay? So there's a question here, it's a very interesting one. Sorry, from Caleb Otudeko. He asks, Nigeria is a very large and diverse group of people, and then he's saying, how can sequencing the various ethnic group and discovering genetic variation and certain findings contribute to global precision medicine? This is very important because when the Human Genome Project was done, African genomes were very limited. And then they now use that for drug discovery findings, and that was a very, very big problem. So now the Africa CDC, along with other partners, including IGH, so they set up a genomic hub to see how they could ensure that African genome, not just Nigerian genome, is incorporated into the global genome project. Because what they observed that some of the drugs that work for the whites and Asians were not working for Africans based on variant. There are some variants, variations in some of the human genome. So capturing all of that will have a better picture. This is an ongoing project. So like I said, IGH is part of the Human Genome Project. So I think in the next couple of years, 54 Gene started something like that, but I think it's like Africa-wide, not just Nigeria. So that's an ongoing project, yeah. Yeah, so over.
All right, thank you very much, Dr. George, for that wonderful session. I just want to add to an answer to the individual who asked about how to avoid errors. For every sequencing run, there is a statistical analysis of bioinformatic requirements, and that is called a Q-score. it shows the quality of the data output that comes out of your sequencing. If the Q score for your data generated is low, your data is as good as useless. So those are one of the things that even publishers would ask of you. That what is the Q score of your data? And what it means is at a particular position that says A, how many it's going to sequence it multiple times. And the more times it's able to say that at point A, let's say it does sequencing about 1,000 times for that point. If you find it in 957 times, then it shows some confidence that A is particularly at that point. So you can reference that. So those are some of the checks. So having said that, thank you very much for this wonderful session. I believe you've learned a thing or two. I will now hand over to either Mr. Gafar or Mr. Chooks to wrap up the session. Thank you very much. Mr. Gafar, are you there? Mr. Chooks, are you there?
Okay, I'm here.
Oh, yeah,
Thank you so much, Dr. George. Thank you so much, Gafar, for the presentation on the monologue. I also want to thank Dr. George for the presentation on the sequencing. Like even me, I learned a lot today. So according to what Mr. Dayo said on the new assignment we gave you guys, so we'll do a follow-up on that on Discord. So, Gafar, is there any other information you really want to pass to the participant before we end this today's section?
Okay, nothing other than I will just take a repetition of what I said earlier. That is regarding teams that have no blender access and what I would encourage you to reach out to us tonight, see if we can set up a meeting with us. Myself, I'll try as much as possible to create time to join any meeting created.
Okay, I think what Gafar is trying to say, there will be a meeting on Discord by 7 today. So the group that said they don't have a Blender artist, I think we need to rectify that and add someone to that group. So I think that's all for now. So we'll get back to you guys on Discord. Thank you so much for your time and have a wonderful day.
Bye, everyone.
Hello. Hello, Mr. Gafar. Hello. Hello.
I can hear you. Go ahead.
Hello. Please, can we get access to the recording?
Okay, definitely. We'll provide that. And you can check YouTube. All live sessions are being recorded on YouTube. So just go to YouTube and we have access to every recording from the day one.
Okay, sir.
So just search for ACEGID on YouTube. You get everything.
Gafar, paste the YouTube link on the chat.
Okay.
Huh? Hold on, let me do it for mine. Mine's not allowed. It's on the desktop. Hold on, let me get it.
Get that laser pointer, hit the reps, like the front of the rim, and that way I know I'm under the ball enough. Great job. You look like a different person there. Wait. Can you do it again?
That's it.
Oh,
What was it? Yes, correct. Laser pointer, elbow to the rim. The quicker that elbow gets to that rim, the easier it is to get under.
those shots.
Great job. Your arc is different when you do that.
So I pasted it on the chat, and it will also be shared in the Discord channel. All right. Have a nice day, guys.